This is a third video in the refraction series lessons. It will focus primarily on refraction and its applications. So to understand this lesson, you need to make sure that you saw refraction part 1, which was on refraction, the speed of light and the index of refraction, and refraction part 2, which was how to draw refraction systems. So incident rays, refracted rays, and seeing some reflection at the same time, in addition to a conceptual understanding of Snell's law, which is a law that allows you to predict what the angle of refraction would be. If none of that makes sense, it means you didn't watch the videos, and you need to go back and do that before you watch this one here. And again, like with the other videos, there are learning goals that you need to make sure that you go through in order to make sure that you've satisfied the learning goals of this session. So by the end of this video, you will be able to understand this picture here in much more detail. You probably already have an idea of what the picture represents, but today our focus is going to be on these applications here. And again, just a quick recap, what we can see here is light from a fish. Now in reality, unless this is a bioluminescent fish, this light is probably coming from the sun, bouncing off the fish, and then bouncing out of the water. As it bounces out of the water, you'll notice that the light ray bends. So I'm going to draw my normal over here. The light ray bends and goes towards the viewer's eye. So this would be the refracted ray. Here's the angle of refraction, and here is the angle of incidence. Now remember, our brain, even though we understand what refraction is, even though we understand what reflection is, we don't realize that refraction is actually happening. So our brain fills in the blank. Our brain thinks that the ray that hits our eye is actually just traveling in a straight line, so it's coming from directly behind. So what we do is we fill in an image with this traceback ray. So just like there were traceback rays for reflected rays in plane mirrors, in some cases of concave and also convex mirrors, there's also traceback rays in the case of refraction. And so we form an image where these traceback rays meet. And so even though the fish is actually over here, when we're, let's say, hunting for the fish with this spear, we will see it up here. So this is called the apparent depth phenomenon, where something just appears a little bit closer to the surface than it actually is because of the refraction of light. So we need to take that into consideration when we're aiming our spear towards a fish. If we aim where we see it, apparently we're going to miss it. So we need to aim a little bit lower, knowing that there's a refraction phenomenon occurring. So the main effects of refraction that we're going to study are apparent depth in spearfishing, which I've already discussed in a previous slide, deviation, so the broken spoon or broken pencil effect, the flattened sun effect, which is something you'll read about in more detail in your textbook, and then total internal reflection and some of the applications of total internal reflection. I'll often refer to total internal reflection as TIR. And not in this presentation, but in the next few lessons, we'll see one of the most important applications of refraction, which is lenses. So we're going to see how lenses work, and we're going to draw ray diagrams for lenses in the following lessons. So apparent depth was already explained to us. You have an object in water. Light ray from that object travels from the water and enters the air towards your eye. As it does so, it changes media, changes from one medium to another, so its speed changes, and it moves away from the normal if it's going from water to air, because it's going from a slow to a fast medium. That's Sarah farts a lot. It goes into your eyes. Your eye does not realize that that bending is happening, so it thinks it's coming from an image that's continuous with the refracted ray. So it just sees it coming directly from behind, and as a result we see the image a little bit closer to the surface, and this is the apparent depth. Even though the object is much deeper, we see it a little bit higher up because of the refraction of light due to the changes in speed as the light from the object goes from water to air, and that happens across various media. So here's a little animation to explain that concept. We have someone in a boat. There's a shark below them. Incident rays from the shark will travel from the water to the air and into the person's eyes. As they travel from the water to the air, the rays will bend, so we'll have a refracted ray, and there'll be a traceback ray to that refracted ray. Same thing for another refracted ray, and wherever the refracted rays, traceback rays meet, that's where the image of the object will form. And so the person would perceive the shark as being much closer to the surface than it actually is. Now, regardless of this, the shark swims pretty fast, so the shark will probably get the person in the boat anyways. So this, again, is the apparent depth of the shark. There actually is a formula to figure out the apparent depth and index of refraction based on apparent depth and actual depth. You don't need to know it, but just know there is a formula and a relationship for almost any one of these concepts that we have discussed. And if you are interested in it, you can learn more about it in grade 12 optics. And again, here's just another picture showing apparent depth. So here is a treasure chest below. We see it a little bit higher up because of that refraction and the traceback rays. Even though we understand that there's refraction happening, our brain doesn't and just assumes that these light rays here are traveling in a straight line without bending. So this is the apparent depth. By definition, it's the depth that we perceive the object to be at, or in other words, the image. The actual depth is where the object actually is compared to the viewer. This is also the reason why, if you've ever gone to the beach or you've ever gone swimming in a pool, if you're standing outside of the water and you're observing someone in the water, their legs appear shorter than they actually are. As you can see, light rays from the feet leave the water, the light rays bend, go into your eyes, but your brain perceives the feet being where the traceback rays intersect, so somewhere up here as opposed to here. So this is because of the apparent depth phenomenon. That's why your legs appear much shorter. A really interesting application of this in the biological world is this fish over here. It actually hunts for its prey, like crickets or other bugs, by shooting water at the bugs. And it observes the insects from under the water. So when it does that, we'd expect some refraction to happen, and we would expect the fish to see the insect somewhere where it's actually not. We'd see them in a different position, so they should be aiming there. But somehow they know to calculate and to account for that refraction of water, and they'll actually aim with a high degree of accuracy towards where the insect actually is. And some people thought, well, maybe it goes directly under the insect so that it's looking along the normal where no refraction would happen. But it doesn't seem to be doing that. It could aim at an angle and still somehow compute for the effect of refraction. So what I'm trying to get at is, if a fish can do this, if a fish can understand the concept of refraction, then you should be able to as well. Take a look at the video at the YouTube link provided. It's a neat video about this fish shooting water at the insects. Quite neat to see, actually. Here's an image of that fish I was talking about, shooting water at the insect. And as you notice, it's not directly below along the normal. It's actually firing at an angle. So there is refraction happening as the light rays from the insect enter the fish's eyes, and it's somehow computing for that effect. Here we can see the broken spoon effect. So if you've ever put a spoon in a glass of water or a pencil, same idea, you'll notice that it seems like the spoon is actually broken. The bottom half is separated from the top half of the spoon, and that's again because of the effect of refraction. So in this image here, you can see the actual spoon. Light rays from the spoon, the bottom half, leave the water. As they leave the water and enter the air, they refract because of the change in speed, and our brain, again, not realizing that refraction is happening, just fills in the blanks behind with traceback rays because we think that the rays are traveling in straight lines only, and we see the image where those traceback rays intersect. As a result, our spoon looks slightly deviated. It's called the deviation effect due to refraction. You can do that with really any object that you put into water. The same thing could be done with a pencil. Make sure you can understand how to explain these effects using the concept of refraction. The flattened sun effect is something I want you to read about in your textbook in some more depth, but it's the idea that when you look at the sun from a certain position on Earth, that the sun looks flat compared to what it would actually look like. And that's because as light rays from the sun travel to the Earth and go through various layers of the atmosphere, there's different densities of the air. And because there's different densities of air, that causes light rays to bend at different degrees. And so as a result, we're going to see the sun based on its traceback rays from the top and bottom position, and it appears flattened compared to what it actually looks like. And that's called the apparent flattened sun effect. Make sure you read about it on page 536, and that you can explain it with the concept of refraction and traceback rays in mind. So now we're going to go on to the concept of total internal reflection. Before we do that, we need to do a quick review of 3 important concepts that we learned about already. The first concept is Sarah farts a lot. So if a light ray goes from a slow medium to a fast medium, it moves away from the normal, so we'll have a larger angle of refraction compared to the angle of incidence, so a larger theta uppercase R compared to our theta I. As you increase that angle of incidence, well, the angle of refraction will also increase. So if I have an angle of incidence of 25 compared to an angle of incidence of 15, the angle of incidence of 25 will have a larger angle of refraction. Basically, the larger your angle of incidence, the farther away from the normal the refracted ray will get. So if I had this angle of incidence here, my refracted ray might be over here instead, with a larger angle of refraction. So those are the first 2 important points to understand. The other point that I want you to understand as well can be very well illustrated in this diagram here, is that along with the refraction that's happening in the concepts that we've been studying, there's also some reflection happening. So if I have an angle of incidence of 15 here and we have a refracted ray over here, well, there is a little bit of the energy from that light ray that's being reflected as well. It's not 100% refracted. So the energy is kind of split in 2 ways. Some reflection, which would go according to the law of reflection. So if that was 15 degrees for angle of incidence, our angle of reflection would be 15 degrees. And then we have our angle of refraction, which we figure out using Snell's law, which you only need to get conceptually. But the main point is that there's some reflection and refraction happening at the same time. So when that occurs, we would call this partial refraction and partial reflection, because there's a little bit of both happening. But we're going to see a case where that actually doesn't always happen. And so this idea of partial refraction and partial reflection is why those one-way mirrors can actually work. So let's say, for example, you have a one-way mirror in this image over here. There you have 2 sides. You have 2 rooms, basically. One room that's well lit and one room that's a bit dimmer. If you have a well-lit room, you'll see a lot more reflection off that one-way mirror, and as a result you'll think that it's just a mirror with your image formed by its reflection. But if you're on the dimly lit side, a lot of light rays from these individuals will go through and you'll be able to see them, and there'll be less of a reflection effect, and as a result you'll see the people on the other side instead of your own reflection. But if both sides were brightly lit, then you'd lose that one-way effect. So again, please take time to review these 3 important points here. Do go over one-way mirrors and how they relate to the partial refraction and reflection concept as well. So now we're going to talk about the concept of total internal reflection. So like I said, typically when light rays go from one medium to another, there'll be a refraction happening because there's a change in the speed of light, but there'll also be some reflection happening at the same time. Now, sometimes at certain angles, what'll happen is the light actually won't leave the water or the medium anymore. It'll actually all reflect instead of refracting. So if you look at this picture over here, you would expect that some light from this laser should leave the water. We should see it in this picture. It should be going up this way. But we don't see that. We see the light ray just bouncing off the surface of the water and staying within the water. So there's no more refraction happening. And that's what total internal reflection actually is. It means that there's no more refraction happening. All of the energy is now going into the reflected ray, and for some reason it isn't leaving the first medium anymore. And that happens when our angle of incidence strikes beyond an angle called the critical angle. And so we're going to see what that means in just a few minutes. So here we have a shark in water, and some of its light rays are leaving the water and going into air, and as they do that, they refract. Along with that, there's again a little bit of reflection, but I'm not showing it there. There's a little bit of reflection happening. Now notice that as I increase the angle of incidence, so this is an angle of incidence here, an even larger one here, the angle of refraction is increasing. So basically, my light ray is moving farther and farther away from the normals represented by these lines here. They should be dotted lines. So when you draw them, make sure they're dotted lines, but I'm moving farther and farther away from the normal. Eventually, I get to an angle where I'm 90 degrees from the normal. This angle of incidence, where my angle of refraction is equal to 90 degrees, where the light ray just rides along the surface of the water or the medium, the interface of the medium, this angle of incidence is called the critical angle, represented as theta c. So at the critical angle, the angle of refraction is going to be 90 degrees. In other words, the light ray will ride along the surface of the interface between the two media, or it'll be 90 degrees to the normal over here. That critical angle really depends on what your media are. If it's water and air, the critical angle will be different than if it was water and honey, for instance. The other thing I want to point out as well is, like I said, there's always a little bit of reflection happening according to the law of reflection. And so the idea is that the energy is split between the refracted ray and the reflected ray. Basically, as I get closer to the angle of incidence, or to the critical angle, more and more energy goes into my reflected ray, and less goes into my refracted ray. So there's less and less going into my refracted ray. We're approaching total internal reflection, but we're not quite there yet. So again, notice the angle of refraction increasing as your angle of incidence increases. Once you get to an angle of incidence where the angle of refraction is 90 degrees, that's going to be your critical angle, where the light ray rides along the interface between the two media that you're studying. Now, if you go beyond the critical angle, so let's say the critical angle was 25 degrees, and you go at 25.1 degrees, no more light will leave the water, no more light will even refract, all of it will be reflected. So at the critical angle, there's still refraction, it's just riding along the surface of water, it's 90 degree refraction. But once you go beyond that critical angle, even by 0.01, then all of it will be reflected within the first medium, and that's when you will have total internal reflection. So not at the critical angle, but above the critical angle. So let me show you that concept. So again, I'm increasing my angle of incidence. As I increase my angle of incidence, the angle of refraction increases. Eventually I get to an angle of incidence where the angle of refraction is 90 degrees. That would be the theta c, in other words, the critical angle. At the critical angle, I don't have total internal reflection yet because I still have a refracted ray. So now if I go beyond the critical angle, I will no longer have refraction. This green here was from the previous one. I no longer have refraction. It's all total internal reflection happening now. So this is beyond the critical angle. I always had some partial reflection happening, but along with that partial reflection, there was some refraction. And same thing here. So there was the refraction, but also some partial reflection, according to the law of reflection. Now at this angle, beyond theta c, so when your angle of incidence is larger than that critical angle, then all of it is going to be reflected within the first medium. So there's no more refracted ray beyond theta I. At critical angle, beyond theta c. At the critical angle, there's still a refracted ray, but as soon as you go beyond that, it's all reflected. That's total internal reflection. So as you can see over here, there's a bit of an error in this diagram. I'll give you a few minutes to try to figure it out, or you could just pause the video and then come back once you're done trying to figure out the error. It really is just an error in terms of what's labeled with the critical angle. So look for that, and then you can come back and see if you were on the right track. You'll notice over here the critical angle is labeled where total internal reflection is happening. If total internal reflection is happening, then that means that we're not at the critical angle, we're actually beyond it. In reality, this should have been the critical angle. This should have been theta c, because you can see that the light ray is traveling 90 degrees to the normal. So whatever textbook made this made a little bit of an error in their labeling. They should realize that theta c is where there's still refraction happening, but this should be beyond theta c. So this is a theta I over here that's actually larger than the critical angle. Now, there's one more condition that's actually required for this total internal reflection to happen, and you may have already noticed it, but for total internal reflection to happen, the first condition was theta I, the angle of incidence, has to be larger than the critical angle. So if critical angle is 25, it has to be something larger than 25. So it could be 25.1, 25.01, it doesn't really matter, something larger than 25. But the other part is that the light has to be traveling from a dense medium, so from a slow medium, to a fast medium. And that's because we want the light ray to move away from the normal so it could eventually form that 90 degrees. If you were going from fast to slow, you would be going towards normal and you wouldn't get that 90 degrees along the surface and going inwards. So the first condition is that the light has to travel from slow to fast to move away from the normal, to eventually get 90 degrees away from the normal. And the second condition is that there has to be an angle of incidence larger than the critical angle, as you would see over here. And again, just understand that there's always that reflection happening along with the refraction. So it's partial refraction, partial reflection. As you approach the critical angle, more and more energy goes into the reflected ray until you get past that critical. Once you get past that critical angle, then all the energy is in the reflected ray and there's no more refracted ray occurring. And to figure out your angle of reflection, you'd simply use the law of reflection, just like we saw with plane mirrors. If the angle of incidence beyond the critical angle was 26 degrees, then the angle of reflection will be 26 degrees as well. Okay, so those are the two conditions required for the total internal reflection to occur. This is just a summary over here of the total internal reflection concept. Over here we can see a laser pointer being aimed at different angles. As you can see, there's more and more energy going into the reflected ray as we approach the critical angle, and then once we're beyond the critical angle, then we have some total internal reflection happening. This would be at the critical angle over here because we have that angle of refraction of 90 degrees, and this would be beyond the critical angle. So the idea is that if that total internal reflection were to occur, you wouldn't see this beam of light over here actually leave the prism because it would be totally internally reflected within. And then it might leave on the other side because it might not hit at the critical angle on the other side. And then you could see it from that position there, but you couldn't see it from any position up here. So you have to take that into consideration in a diagram like this. So this is a summary of total internal reflection. We can see the two conditions that are required for total internal reflection to occur. Light has to go from an optically more dense medium, so a slow medium, to a less optically dense medium, to a fast medium, in other words, so it can move away from the normal. The refractor ray can move away from the normal, and the angle of incidence must exceed the critical angle. If you say must equal the critical angle, then you're wrong. It's not total internal reflection because there's still refraction occurring. There's a video that you can watch in order to see a lab experiment that was done to illustrate the concept of total internal reflection, and this diagram sums up the concept in some great detail, showing both conditions and showing that there's some partial reflection, and some partial refraction occurring until eventually we get to a point where there's no more refraction at all and it's all reflection once your theta I is beyond your theta C, which is your critical angle. There is a formula to calculate critical angle, but again, that's one of those concepts that you'll learn in grade 12. We are learning it more conceptually at the moment. You should be able to draw a diagram illustrating this concept, and you should be able to understand when the total internal reflection would occur, but you don't need to know how to calculate it for now. And again, here's just a summary with a semicircular block showing the process of total internal reflection in progress. So you can see over here that we've actually reached the critical angle because we are refracting 90 degrees to normal, and here we've gone beyond the critical angle because now there's total internal reflection. Notice how we are greater than the critical angle. That's a bolded word here, so please make sure that you pay attention to that. So we'll do a few practice problems to make sure you understand the concept. This one's in your worksheets, your learning goals, but I will do one or two of them with you so you understand what's going on. So the three diagrams below show light traveling through two different media. In which diagrams would total internal reflection be possible if the angle of incidence were increased? Explain. So we're basically asking for the conditions of total internal reflection. Let's take a look at question A. Notice we have a light ray. Here's our angle of incidence. Here's our angle of refraction. You'll notice that the light ray, as it went from medium A to medium B, moved closer to the normal. Remember that for total internal reflection to happen, you need to be in a medium where the light ray moves away from the normal. You need to be in a Sarah farts a lot situation. But right now, we are in a freaky science teacher situation. We are going from a fast to a slow medium. For total internal reflection to happen, one of the conditions is that you have to go from a slow to fast medium in order to move away from the normal. But if you're in a fast to slow medium, you move towards normal. And so in this case, total internal reflection could not occur because you're not satisfying condition 1. Let's take a look at B. Here's our angle of incidence. So make sure you look at these arrows because they tell you what your incident ray is and what your refracted ray is. Here's our angle of refraction. As you can see, the angle of refraction is larger than the angle of incidence, which means we're moving away from the normal. So in this condition here, we are doing an SFA. We're going from a slow to fast medium to move away from the normal. So if you increase the angle of incidence enough until you go beyond the critical angle, then yes, eventually you could see total internal reflection in this diagram here. You don't see it right now. You see some refraction. There's probably some reflection occurring as well, but it's not total reflection. But it is a diagram where there's potential for total internal reflection to occur. So I'll leave C for you to try on your own. And now we're going to take a look at how to represent a diagram with total internal reflection. I want you to try these ones on your own first and come back and check your answers once you've actually attempted them. So the critical angle for the surface between honey, optically dense, which has a high N, and air, less dense, so a low N, is 25 degrees. And I just made that up. It's not actually the real critical angle. There is a formula to calculate it, but again, you don't have to know how to do that. So I just made it up for this problem. Draw a ray diagram to illustrate what occurs when in the following situation. So we're going to do one ray diagram for A, B, and C. So an incident ray travels from honey to air with an angle of incidence of 25 degrees. So your first step is to draw the surface, the interface between honey and air. And then what I would do is I would draw a normal 90 degrees to that surface, to that interface. Draw where honey is. So what I would do is I would write N honey for the index of refraction of honey. And then I would put NH2O if my H2O is above. You could have done it the other way around. It doesn't really matter as long as your arrows are going in the correct direction based on the problem. You're told that the angle of incidence is 25 degrees and you're going from honey to air. So if you're going from honey to air, and you would measure this with a protractor from the normal, so my angle of incidence is 25 degrees. Make sure it connects where the normal meets the interface, and label this as 25 degrees. So theta I is 25. Now, because you know that the critical angle is 25 degrees, you know that the angle of refraction must be 90 degrees. And it makes sense in this situation here because we're going from the dense medium to the less dense medium. We're going from slow to fast. So it would be 90 degrees to the normal over here. It's not total internal reflection yet, but we're approaching that. If we went beyond this, we'd be at total internal reflection. Let's try to solve for diagram or scenario B. So in scenario B, I'm going to do the same setup. I'm going to do my interface here between honey and water. My normal 90 degrees to that surface. You would use a ruler, of course, and yours would look a lot neater than mine. And we have an incident ray that travels from air to honey with an angle of incidence of 25. So, oh, and I should have said air in this problem. So we'll cross NH2O out and we'll put air over here. It would have been the same effect because honey is just more dense overall than water. So in this case, I'm going to leave air on top. And I'm going to leave honey at the bottom. Honey still has a higher index of refraction than air, so it's the more dense medium. And this time, though, the light ray is traveling from air to honey. So my incident ray needs to be coming from the top here. Label that as theta I is equal to 25. Now, the thing is, in this case, we are going from the fast medium to the slow medium. So we're not moving away from the normal. So if you drew this 90 degrees from the normal, you would have done this incorrectly because we're going from fast to slow. So in reality, you wouldn't actually know what the angle of refraction is. You could just predict that it would be the angle of refraction would be smaller than the angle of incidence because it would move away from the normal. This is a freaky science teacher situation. It might be 15 degrees, it might be, I don't know, 17 degrees. There's a formula to figure it out, again, called Snell's law. But the point is, I want to see that you drew it closer to the normal as opposed to farther away from the normal. So you have to read the question carefully because in this case here, it was going from air to honey. So now let's take a look at the last scenario. In the last scenario, we have a light ray traveling from honey to air with an angle of incidence of 26 degrees. So now we'll draw the interface between honey and air. We'll draw our normal, 90 degrees to that interface. And we're going to draw our angle of incidence of our incident ray with an angle of incidence of 26 degrees, and you can label that angle of incidence theta I is 26 degrees. Now, from the question, we know that the critical angle is 25 degrees. 26 degrees is larger than the critical angle, which means there's no more refraction happening, and that we're going to have total internal reflection occur because we are going from the slow to the fast medium. Again, let's label our media over here, N honey, N air. And so now it's a simple law of reflection problem where we simply draw the reflected ray according to the law of reflection, which means 26 degrees from the normal. And you would use a protractor, which means you would be a lot closer than I would be. So now we have total internal reflection occurring 26 degrees. So you have to read the question carefully to make sure that you know that there's total internal reflection occurring, or that you know that it's not going to happen. So I want you to quickly watch the demonstration done at this video link here. You'll notice a laser pointer shining through a bottle of water with a hole in it, and the beam of light from the laser will stay trapped within the water that's leaking out of the hole from the bottle. That there is an example of total internal reflection. That beam of light is striking the water beyond the critical angle so that it stays within that stream of water as it goes down, because again, it's going from water to air, and water is a more dense medium than air is. As a result, total internal reflection can occur if you have the if you've exceeded the critical angle. Now we're going to take a quick look at some applications of total internal reflection. One of the most interesting applications, which I do want you to read up on in your textbook in more detail, is diamonds. So the reason diamonds shine so much is because of the concept of total internal reflection. There are several cuts placed in the diamonds so that the diamond can actually have a very small critical angle. If your critical angle is very small, then there are many angles that can be larger than it. So if I had a critical angle of, let's say, 20, then an angle of incidence of 21 is larger than that, and we can have total internal reflection occur. So when the light ray enters a diamond that's cut appropriately, it'll do some total internal reflection rather than going straight through like you see over here. It'll actually bounce within it and then bounce right back out to the observer's eyes. So what you're seeing is a whole bunch of light just bouncing within the diamond and bouncing back out to your eyes, which makes the diamond extremely shiny to you. And that's all based on the idea that there's a high index of refraction for diamond, and air has a low index of refraction. So when the light rays try to go from the diamond to the air, the concept of total internal reflection could actually happen. Here we have a low N in the air. And again, because of the cuts, the light rays are more likely to strike beyond the critical angle to make total internal reflection occur. And so you can see that from this animation. Let's go back to our slide here. So again, based on the ideal cuts, if you have an ideal cut for a diamond, you're going to get a lot of that total internal reflection in order to give you that nice sparkly look that the diamond gets. If the cuts are too shallow or too deep, it's less likely that you're going to strike beyond the very small critical angle, and as a result you won't get that nice sparkle that you'd expect to get from a diamond. So the better the ideal cut gives you more total internal reflection, which gives you a more ideal shine to it. So now we are at another application of total internal reflection, which is called the fiber optics cable. It's basically a very, very small glass fiber. It's extremely thin, and the fiber optics is basically used to transmit information from one area to another. And we transmit the information while using light. So light can go through this glass fiber optics cable and hit beyond the critical angle many times due to its shape. And as a result, the light will continue traveling within until it exits on the other side. So we have the source of the signal over here, and here we have where we want the signal to be sent to. So we can use that for telephone signals, computer signals, and it's better than using the electrical wires, less chances of electrical interference, of fires, a much safer and also a much quicker solution to sending signals from one area to another. And so we're going to go take a quick look at the anatomy of the fiber optics cable so you can understand why total internal reflection can occur within this cable. So there are a few parts to the fiber optics cable. You have the buffer coating, the cladding, and then the inner core, and they're made of different materials, so I want you to read up on that. We're going to go take a look at the next slide to see how they're arranged based on their index of refraction so that total internal reflection can actually occur. So if we look over here, we have two choices. We have our cladding and we have our core. Now, the index of refraction for the cladding and core could either be 1.62 or 1.52, and we have to place where they actually go. So remember that total internal reflection can only occur if you're going from a slow to a fast medium, right? You want that SFA scenario. So what that means is you need to go from a high N to a low N medium. High N means slower light. So for total internal reflection to occur, so for the light not to go from the core to the cladding, you need to make sure the core has a higher N. So the core should have an N of 1.62, and the cladding should have an N of 1.52, so that when we do strike beyond the critical angle, then total internal reflection will occur, and that signal stays trapped within the cable and can only escape once it gets to the other side, where the reception of the signal would be ideal. Other applications of TIR work in a similar fashion. The endoscope used by doctors in order to see your organs. So basically there's a light source. There's the doctor's eye over here. We use cables that we transmit the light source through. They have some total internal reflection that occurs until the light reaches your organ. It bounces off the organ through another little cable over here, and then it goes to the doctor's eye or to a screen where the organ can actually be viewed in some way. And that's called an endoscope, which also uses the concept of total internal reflection. Other applications I do want you to read about include the triangular prism. So a prism is basically a piece of plastic or glass that light rays can pass through. And based on their shape, they have a critical angle of 41.1 with air. So if you strike beyond that, then you have total internal reflection. So here we have a light ray that strikes at, let's say, 45 degrees, which is beyond 41.1, and it will reflect within at also 45 degrees based on the law of reflection. And it might exit the other side because here it's not hitting at the critical angle. It did at this point, but not at this point here. So it can exit over here. Keep in mind that total internal reflection would not happen as you're going from air into the prism, because that would be a fast to slow. You want a slow to fast, which would be your air out here. So slow is the plastic prism, to fast, which is the air, to move away from the normal and have that total internal reflection. And these prisms can be used in a variety of different applications. For example, we can use a triangular prism in a periscope. We saw plane mirrors to make a periscope, but prisms actually are a little bit better when you're trying to make a periscope, and I want you to read up on why that is. And we also use these prisms in binoculars. So there's total internal reflection, as you can see, occurring here. This would be the object you're trying to view, and then this would be your eye over here. So you'd be viewing the object with your eye over here, and the reason the light ray from the object was able to get there is because of these triangular prisms doing total internal reflection between the two, and then finally reflecting the object into your eye. And they're placed in such a way that the light rays will strike beyond the critical angle so that total internal reflection can occur. So that beyond the critical angle is happening here, and then here, and here, but not at the parts where they actually go through. Total internal reflection can also be used to explain the concept of mirages and shimmering. I do want you to read up on that to understand how mirages and shimmering work based on the concept of total internal reflection. And the idea is that you have light rays basically traveling within the air, but the air itself might have different optical densities because of different temperatures. So the air, for example, closer to the ground might be a little bit hotter because the ground is hot, which gives it a different optical density and causes bending of light, and as a result you might see an image where there actually is no object. So I want you to read up on the concept of mirages and just write some brief notes on it to make sure that you understand how total internal reflection and refraction actually apply to this concept. So to finish off, we're going to take a quick look at how rainbows form. And you'll notice that rainbow formation actually takes into consideration many concepts that we saw throughout the optics unit so far. So here we have a ray of light from the sun. So it's white light made up of all the different colors of the rainbow, Roy G. Biv, as we learned in the first few lessons. Here we have a raindrop. The white light enters the raindrop, so some of it will go into the raindrop. Some of it's reflected, of course, because there's some partial reflection and refraction happening. But you'll notice that as the white light goes into the raindrop, the different colors of light will bend to different degrees, and that's because the different colors of light actually travel at different speeds in different media. So some colors of light will bend more than others, and that's what causes the separation of the different colors of light. So we have some refraction happening, which is the bending of the light, And because the different colors travel at different speeds, they bend to different degrees, and as a result, the different colors disperse from each other. They separate a little bit more from each other, enough for our brain to actually be able to tell them apart. And that concept is called dispersion. So it's a separation of the different colors of light because of the different degrees of refraction or bending that's occurring. Following that, you'll notice that rather than leave the raindrop, there's total internal reflection that occurs because we're in a water droplet, which is more dense than the surrounding air, and we're hitting beyond the critical angle. So that happens at this point over here, point number 5, total internal reflection. And then we have some more basically dispersion happening as we exit the raindrop. Because at this point here, we're not hitting beyond the critical angle, and so these colors can actually exit and disperse and refract some more, again, to different degrees because they're different colors, and that separation allows us to see a rainbow. Now, in reality, you wouldn't see a rainbow from a single raindrop. You'd actually have many raindrops separating these colors, and that's what would be that would be responsible for the order of the colors that you see in the rainbow. For more details on the order of the color, you can just read up in your textbook or watch a video on rainbows, but I want you to get the concept that we have primarily some refraction separating the colors of light, which is called dispersion, and then we have some total internal reflection occurring within the raindrop, and then some more refraction and dispersion occurring near the end. So we see all the behaviors of light, or the majority of them, in this rainbow formation. And the reality is there probably is some absorption occurring as well. Some of the energy from the light will be absorbed as heat, but not all of it. So all the behaviors can be summarized within the concept of rainbow formation. Here's your homework. Please make sure you do your readings, page 526 to 531. Do the questions on 531, 1 to 5, and 7 to 9. Same thing with 535 to 539. Do questions 1 to 7. And then there's some extra worksheets that will be provided to you. You can complete those. And there will be a PhET simulation sheet that will be handed to you so you can learn the concept of refraction and total internal reflection in some more detail. You will also be responsible for knowing how to do a lab to figure out the critical angle, and we'll have some more information on that in class.